Welcome and thank you for tuning in to the second day of our 2021 Landscape Faculty Academy webinar series and the Backflow Prevention for Landscape Irrigation session. Before we get into our housekeeping notes, I would like to thank our sponsors, Rainbird, Hunter, Ewing, and Brightview for helping make this event possible. A quick moment for some housekeeping notes before we get started. I have muted everyone by default, so we won't be disrupted by any latecomers. Please keep your microphone muted throughout the presentation unless you have a question, as this will help minimize any background noise. During the presentation, if you have questions, you can ask verbally or via the chat box. Our speaker will have breaks throughout the presentation where we will address questions from the prior section. Without further ado, I would like to welcome our speaker, Paul Waite.
Thank you very much, Nicole. Welcome to Backflow Prevention for Landscape Irrigation. Nicole, is everything looking good on your side before I get going?
Yeah, if you want to just go ahead and share your screen, I think we'll be good to go.
Okay, thank you. I believe that would be the right screen for me.
Looks good.
Perfect. Thank you so much. Again, welcome to Backflow Prevention for Landscape Irrigation. We are looking at specific backflow preventers, what we call testable backflow preventers, that are used in the landscape industry for a variety of purposes. So they're going to be on drip systems, they're going to be on turf sprinkler systems, as well as other types of applications for landscape irrigation. So getting started today, it's just, we got some muting going on right now. If you do unmute, remember background noise does affect everybody. If you have some on-hold messaging, please don't put your line on hold because that gets the broadcast usually to everybody. And we'll have some designated Q&A times or enter something in the chat, just like Nicole mentioned. If you want a copy of my presentation electronically or want to connect with me, I'm on LinkedIn. You can connect with me there. I have an email address of paul.waite@zern.com. In addition, we have a One Zern channel on YouTube, and there's a pretty good irrigation playlist out there that has a lot of really good videos to back up some of the material that I'm presenting here. And there's a lot of ways to get connected. So just shoot me an email and I'll send you a PDF copy of the presentation. I know a lot of you already have hard copies or you were given a PDF version of it. I can always get you another if you need that as well. So today we're going to cover backflow prevention basics. So this is like the Backflow 101, and that kind of goes over a high-level view of how backflow is looked at from not just only a code perspective, but how it applies to the rest of us when we're working with backflow preventers and backflow prevention in the field. Then we're going to cover RP, reduced pressure principle, and pressure vacuum breaker operation. Very important to know the distinction between these two products, these two types of backflow preventers, because the installation requirements that we'll cover in the third section basically relate right back to those operation characteristics of these valves. And then we're going to look into selecting an RP versus a PVB. There are some control issues there with the installation, and we need to make sure we know when an RP should be selected and when a PVB is not the appropriate backflow preventer for the application. And then we'll lightly cover some freeze protection and maintenance for backflow preventers. And then of course we'll have a Q&A at the end. But in each section, when I complete each section, we'll have a little opportunity there to do a little Q&A. So backflow prevention basics. Plumbing codes require backflow preventers to be installed, and they're installed to protect our drinking water system. This was all put together by the federal government back in 1974 with the Safe Drinking Water Act, and that's where it all stems from. But the federal government never really took ownership of this. They said, okay, you states this act we're going to pass, you states need to find a way on how to get this code, excuse me, get this code down to your population. And then some of the states said, okay, fine, we'll go ahead and make a state code, and then that state code becomes what is basically used throughout the state. Texas is one of those states. They have the Texas Commission on Environmental Quality, TCEQ. They call the shots. However, those states also delegate the Safe Drinking Water Act down to counties, cities, water purveyors. So companies like American Water, who's a big water wholesaler out there, they are the water purveyor. They get to basically dictate how these codes regarding backflow prevention and cross-connection control are put into the marketplace and what the requirements are. So that would be considered the authority having jurisdiction. And this authority, it could be a different authority on one side of the street versus the other side of the street, county by county, definitely state by state. After you spend decades in the backflow industry in the landscape irrigation market like I have, you realize very quickly that it varies greatly across the country. What is code in California is certainly not code in Arizona or in Nevada. Definitely a different code when you get out into Florida and into the Carolinas and the New England states. Even up here in Idaho, where I live right now, the code just recently changed about 4 years ago. So these are always evolving, and the codes have a tendency to move towards more aggressive backflow prevention. In other words, more enforcement, a higher level of backflow prevention. And the reason being is we uncover over time problems in our water system with the connections to the landscape irrigation, and they require a code update periodically. So what is backflow? That's the big question. A lot of people think backflow is, is one thing and it could be another thing. But what it is really is it's just the reversal, the unwanted reversal of flow of water. It's water and a mixture of that water with any kind of substance that's flowing backwards from anywhere into our potable water supply. And it can be from any source as well. So it's basically bad stuff that we don't want in our potable water supply that we're connected to. So backflow prevention is very important because it protects our drinking water, our potable domestic water supply from contamination, and it also provides water conservation. If a water line breaks or something like that and they issue boil water orders, or if there's a backflow incident and there's a contamination situation that occurs, they've got to flush the entire line, so there's a lot of water wasted in those situations. But also liability mitigation. It's a very big thing. Pollution is a very big thing across the world for lack of any other perspective. But specifically in the U.S., we have a lot of legal stuff and legal wrangling going on constantly. And so the liability mitigation becomes very important. There is no insurance that you can buy to back you up if you contaminate the water supply. It's an out-of-pocket expense, a big legal fight, and it always happens to go in one direction, and usually that's the EPA wins and everybody else loses. And the reason why is because protecting the water supply has been dictated since 1974 in the Safe Drinking Water Act. This is not something that's unknown, but there are municipalities and water districts out there that don't take it seriously, or they don't enforce the code that they have on the book. And that's a really big deal. And that's why liability becomes such a major component in all of this. So when we started talking about backflow prevention and stuff, some of the definitions that we need to know is what is a cross connection? And a cross connection is any connection, basically. It's any potential connection or any actual connection. And it's unprotected, and it could be protected as well. Sometimes protected connections are not protected well enough. And any substance can get through these connections to get into our water supply. So when we think of a cross connection, we think generally a direct physical connection between two piping systems. We have some images on the screen here that kind of give an illustration of what we're talking about here. I mean, just the standard irrigation system with a bunch of zone valves, that is nothing but a big cross connection situation, right? A couple garden hoses sitting in a swimming pool is also a cross connection. It's an indirect cross connection, but nonetheless, it is a cross connection. They call it potential. Autofill on a fountain, Siamese or Y connection on a hose bib like that. Those are all cross connections. And when we start thinking about our distribution system in North America, it is nothing but one big cross connection. The houses we live in are one big cross connection. So we have cross connections everywhere in our daily lives and in all our systems. That's how we deliver water in North America. We deliver it through cross connections and pressurized systems. Two types of backflow conditions that we need to be aware of. One is back siphonage. Now, this happens when in your supply line, there's a negative, a subatmospheric, or a very low pressure situation in the supply line versus what is happening downstream. And that supply line pressure starts dropping or it goes negative, and the water downstream is siphoned or sucked back out into the domestic water supply. And pipeline breaks, when they occur, it's a big opening in the main line, and all the water in that grid rushes to that area, creating a massive back siphonage event. And firefighting does the same thing. These high water withdrawal rates where fire trucks pull up to the fire hydrant and they connect and they start pumping, pump, 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 pump. They're pulling water out of that entire grid as much as they need in order to put out that fire. And that creates a back siphonage event in that grid, in that region. So you think about a big fire, 6 alarm, 7 alarm fire, where you have all of these trucks pulling water from the same grid. That entire grid and even the connected grids could suffer back siphonage events. And if there's not backflow preventers on those lines, you're going to get water, possibly contaminated water that's back siphoning into the domestic supply. Now, back pressure is another backflow condition, and this is a little more straightforward. This is basically pressure downstream. Basically, your supply line comes in and the water flows what we call downstream. And that water in that property or in that situation is higher than the supply line coming in. So for example, elevation in a piping system, you got a big high-rise building or a big hill or any type of small hill, you're going to generate some head of pressure that's going to push back against your supply line pressure coming in. Also a pump. We put pumps on our system for irrigation. We're going to pump up the pressure. That pump could generate a downstream pressure that's higher than the pressure coming in, which is why we put in the pumps. And now we have a back pressure situation. These two conditions, back siphonage and back pressure, are very interesting, and they're necessary to understand these definitions in order to know about the different types of backflow preventers we use and their installation requirements, which we'll be covering later. So degree of hazard is pretty easy here in North America. We only have 2 degrees of hazard, low hazard and high hazard. Low hazard is basically anything that can get into the water that does not cause sickness or death. So it could be impaired by the sight or the taste or the smell. It is a pollutant generally, but it's a non-health hazard. So that's low hazard. High hazard is the skull and crossbones. It can cause sickness, it can cause death, but it could have the same water quality impairments or none water quality impairments. For example, a biologic, you might not even see it or you can't taste it. There's no smell to it, but a biologic can hurt you, cause sickness, cause death, and it is a health hazard. It's considered a contaminant. So we have our cross connections and we have backflow conditions. We have back siphonage, back pressure, low hazard, high hazard. We have all these definitions, and now we're going to take these definitions and we're going to apply them to the backflow preventers that we use today in the landscape industry. So the 3 categories, we've got reduced pressure principle assemblies, RP, RPA, or RPZ, as they say. RPZ is a pretty common phrase. In Canada, they say RPZ, just to kind of get everybody who's in the very north up there to be inclusive. Double check valve assemblies, double checks of DC, DCV, DCVA. We see these terms on specifications, and then pressure vacuum breakers are always considered PVBs, and I've never seen them any other way than that. Now, these backflow preventers are testable. They're repairable inline, and they're isolatable. They have shut-off valves on them that you can isolate these backflow preventers. It's very unique. So when you look at these conditions that we have, the back siphonage, back pressure, low hazard, and high hazard, and we apply them to these three types of backflow preventers, we see that the RP is the one-stop shop. It covers everything: back siphonage, back pressure, low hazard, high hazard. And that's one of the backflow preventers that we see codes across North America moving more towards an RP being required than anything else. And the reason why is because it can handle anything that's thrown at it. Unfortunately, it also has to be the most expensive of the backflow preventers that we're talking about here. Double checks, which are still used in a lot of regions around the country. Probably I'd say 6 or 7 major states still use double checks. They're still in the code. Back siphonage, it can handle back pressure, but it is only considered a low hazard backflow preventer, which kind of makes you wonder, and you have to ask the question at that point: is landscape irrigation a high hazard or low hazard application? And I would say that you would have to depend upon your perspective. And that means, are you putting chemicals in your landscape, whether it's pesticides, herbicides, or just general fertilizers? Would you consider those chemicals a health hazard? And you have to say, yes, if I ingest that stuff, that's probably true. They are a health hazard. So it would be considered, irrigation should be considered somewhat of a high hazard application. But double checks are still used. They're still coded in many places. A lot of the states that still use double checks, over the years, they've been looking at moving those codes towards a more high hazard type backflow preventer. That's what happened here in Idaho 4 years ago. They eliminated double checks from the code, no longer allowed. Everything's grandfathered in, but now the code here is RP and PVB. And the PVB, the pressure vacuum breaker, it is a high hazard backflow preventer. It can handle low and high, but it cannot handle back pressure. You're not allowed to back pressure those valves. So they can only be implemented in applications where back siphonage would be the backflow condition that they could experience. That's very unique, because if you look at the RP versus the PVB, both high hazard devices, that's the direction codes are going. Now you've got to know when to put in a PVB versus when to put in an RP. And that's why in my presentation, I have a section later that says, when do we select an RP over a PVB? And we'll cover that here in a little bit. So let's take a look at what some of the PVBs look like. These are the ones that Zurn offers. These are different models we've got, and so we've got compact versions, heavy duty versions have been on the market, lead-free, freeze-resistant versions, lead-free, spill-resistant versions, and most manufacturers have these same types of backflow preventers in the pressure vacuum breaker category. And this is kind of what they look like. I mean, they've all got similar looks to them. They have an inlet from the bottom and a 90-degree outlet that goes out from the side. Whether they go right to left or left to right doesn't matter. This is how they all look. I've never seen a PVB that doesn't look anything different than the way these look right here. So it's a pretty good example of a good mix of pressure vacuum breakers on the market. When we get into double checks and reduced pressure valves, we have to start looking at things maybe from a different point of view. One of the points of view is it an all bronze unit? So there are some all bronze units. We have like in the top corner over here, we have a all bronze RP unit, been around in the market for a long period of time. That's our typical 975XL, and there's other manufacturers out there that make very similar type of valves. And then we've got some double checks that are all bronze right here, our whole 950 series in the middle. And these are just typical all bronze, cast bronze products, you know, older styles, been in the market a long, long time. And they're tried and true. It's just cost of bronze and the cost of these types of materials and function on these. You know, it hasn't changed in 20, 30, 40 years. So when you want to move to an upgrade, what do you have to consider? You have to consider what's available on the market. And so there are some new products like the Model 375 RP here, and then the 350 double check here that I'm circling as well. These are hybrid products that are hybrid bronze with a removable plastic pressure vessel, which is a glass-filled nylon composite material, very strong. And it's really interesting to see the evolution of backflow preventers moving from all bronze to somewhat of a hybrid product. I get a lot of questions from people saying, how come you guys don't make an all plastic version of backflow preventers? And there's reasons on that. A lot of that has to do with the codes, specifically plumbing codes. Plumbing codes require metal end connections for plumbing systems. And if we were to go down a path of making all plastic backflow preventer, we just make it only for the irrigation world, and that would be something that would be not in our product management scope. We're trying to address all markets with the designs and the materials that we use in our backflow preventers. So it's pretty interesting when you look at things from a product development side. You have to satisfy the fire protection market, the plumbing market, the waterworks market, and the irrigation market, all with the same backflow preventer. So that's kind of how we stand on the backflow preventer side versus just making all plastic versions. So let's talk about the RP and PVB operation. This is pretty interesting because this is where you got to put on your thinking hats just a little bit, because we're gonna do some analytics with some pressure drops and kind of see how water moves through both an RP and a PVB. We're not going to address the double checks operation because it really is very simple. It's 2 checks in line, and that's about it. And each one has a drop. But the RP and PVB are the critical backflow preventers for understanding operation, because they have some installation requirements that are very different. So here's another side view of our 975XL. We got some major components here to identify, and I'll just start circling them right here. We got our number 1 check valve. It points up. Generally, in any Y pattern backflow preventer, the number 1 check is always the one facing up. And then the number 2 check valve is the one that sits facing down. It's just the nature of how these designs are put together, and that's natural for any of these Y patterns. They're all very similar. So those number 1 check, number 2 check. We also have a number 1 shutoff valve. It's a ball valve. And we've got a number 2 shutoff valve, and it's a ball valve. So that's your inlet and your outlet shutoff. And they're just quarter turn ball valves, and those are standardized across all backflow preventers in the 2-inch and smaller specification category. They all use quarter turn ball valves by the code definitions for developing backflow preventers and manufacturing backflow preventers. Interestingly, we have this relief valve down here on the RP. This is where water comes out, right down here. And this is what is annoying to a lot of people, because when these are installed incorrectly or they have problems, water always comes out, and that's a big issue for conservation and for other reasons as well. It's just water wasting. Just want to point out one real important feature here that a lot of people don't realize is that right in this area of the backflow preventer, there's a sensing tube, and this is very important for all RPs have this, but it's very important to understand because we're going to identify it in the next couple slides and what the function is. And what its function is it takes the high pressure that's coming in the inlet and it puts it on the backside of this diaphragm, which closes this relief valve. And so when we get into this operation on the next slide here, we're going to identify these components again. So this is an RP in a static condition. It had been flowing, and now we just turn the water off and it's just sitting here. And as you can see, we're using some pretty easy numbers here. We're saying we have 100 PSI on the inlet. We're saying that we have an 8-pound spring right here in the number 1 check. So that takes 8 PSI to open up that spring. So the pressure drop across that check is 8 PSI, which makes us have 92 PSI in this teal colored reduced pressure zone. So that's the reduced pressure zone. Okay, so we got a 100 and 8 PSI drop, 92 in the zone. Now we have the sensing tube right here, the one I identified previously, which allows this high pressure to come down here and fill this area behind the diaphragm, and it closes that relief valve. That relief valve, when there's no water in this, and this valve is sitting in the box, is normally open. It is open. It is water and air can flow right across that relief valve check. Not a problem at all. That's how this is designed. And when we pressurize it, the diaphragm and this surface area and the high pressure is enough to close this spring. And the spring in the relief valve is just a 2-pound spring. It's very small. It's only there to basically work in conjunction with that high pressure side and allow this valve to execute its differential pressure status and operation so that this relief valve functions correctly. So when we look at this, we have a 2-pound spring in the relief valve. We get 92 PSI in the zone. So 92 plus 2 is 94. So this relief valve is closed because we have 100 PSI pushing it closed and 94 PSI pushing it open. 94 being smaller than 100, that loses and the relief valve remains closed and there's no water coming out. Last spring we have is the number 2 check. So this is our number 2 check. It has a 2 PSI spring. And so our total drop across this valve in a static condition is 10 PSI and we got 90 PSI on the outlet. So I want to make sure that that's clear with everybody because this is a very important function to understand the static condition for this backflow preventer, specifically the relief valve and how the diaphragm works with the spring. So now we're going to turn on some water and we're going to flow this valve. So there we go. The checks are open. So the number 1 check is open right here and the number 2 check is open right here. No change in the valve. So ideally, we're going to go from flowing condition back to the static condition. Everybody's happy. All the metrics in this valve still remain consistent. Now, there will be some additional losses on the outlet due to the flow characteristics. So as more flow goes through the valve, you're going to get pressure losses. So 90 PSI could easily start dropping to 89 and 88, even as low as 85. You could get a 15 PSI drop across an RP flowing a lot of water without any issues whatsoever. So now here's the thing. We have a little rock that came into our water system, or a little ball of T-paste or Teflon tape or whatever, little grab piece of sand, is going to come down the line and we're going to have that get lodged in the number 1 check. So the next slide here, we've got static condition. We turned off the water. There's a little rock right in this area. You can see that little rock probably right there. So that's stuck in the number 1 check. And like I said, it could be anything. It could be a piece of sand. It could be a ball of T-paste, blue glue, whatever. It's stuck and that number 1 check is foul. So that is a big deal because now we've just disrupted the reduced pressure zone. The water pressure on the inlet and the water pressure in the zone equal each other because this water is good. High pressure is going to creep across the check valve and the zone is going to have the same pressure as the inlet. So now we start looking at the relief valve and we say, well, we've got a 2 PSI spring in the relief valve trying to push it open. And we only have 100 PSI now trying to close it, but we also have 100 PSI in the zone. So we end up with 102 PSI in the reduced zone and the relief valve opens up. And that's how relief valves operate. When you walk up to them and you see them dripping water and they're dumping a lot of water. This is what's happened, is this equilibrium in the differential pressure situation between the 2 check valves, the number 1 and the number 2, along with the relief valve spring. We now have water coming out the relief valve due to a foul in the number 1 check. And 99% of the time that there's water coming out of the relief valve, it has something to do with the number 1 check. A lot of people will go into the relief valve and start repairing it, but the bottom line is it's something to do with the number 1 check. It could be a problem with the poppet or the seal or the seat. It doesn't have to be a rock. It could be anything to do with this check that's causing some disruption to allow the high pressure to move across the number 1 check and put the high pressure into the zone. And when you add the 2-pound spring from the relief valve, you end up with the relief valve opening. Now, one important thing to remember here, and this is probably a critical point for observation and troubleshooting purposes, is that the amount of water coming out the relief valve is directly proportional to the extent of the foul across the number one check. If that relief valve is just dripping slowly, you know, a drip every 2 seconds, the foul is pretty small on that number one check. Something small is happening that's causing that. If a lot of water is coming out, you know, something big is going on. If it happens periodically, like every other day or on Sunday morning at 4 a.m., you know that there's something occurring at that point in time that could be system related that number one check is reacting to, because there's only one way really for water to come out, or actually there's two ways for water to come out out that relief valve. The number one way is something going on with the number one check. There's something going on with this number one check that is causing relief valve discharge. If we got a foul on the number two check, there's water going to come out there as well. But in order for water to come out the relief valve on a foul number two check, you got to have some back pressure to push it through there. If the system is off and there's no back pressure downstream and the water's not flowing, there's a very low probability of any water coming out the relief valve through or across the number two check. So just remember, when there's water coming out the relief valve, there's something going on with the number one check, whether it's a system level issue or whether it's a rock or a foul like this. That is exactly the way we have to look at this. And that's where the service goes. It goes the number one check. You do not service the relief valve when the relief valve is dripping. You know, I have a little adage I put together, and I said, you know, my car stopped working. I was stuck on the side of the road, so I replaced my motor. And then I only found out later that I was out of gas, right? That's kind of, you know, the same thing with the backflow preventer here. You don't just take apart the relief valve to fix the relief valve problem. You got to go into the number one check all the time. So that's a good tip for anybody doing maintenance out there. Now let's take a look at the pressure vacuum breaker and how it differs greatly from the reduced pressure principal backflow preventer. So here's a typical PVB, and it has a lot less components, but some similar components. We've got our number one shutoff valve, or number two shutoff valve. We've got a canopy on top here, a bonnet, an air inlet valve. There's the check valve is usually down in the base area here. We got some test cocks, just like everything else. Water flows up, like I told you, it flows up this direction, and then it flows out from the side like this. And these are really simple valves. And if you look at them, there's only one check. This is a single check backflow preventer. It's just one check valve in a seat, but it has an air inlet valve that's spring loaded that seals up against this bonnet. And that is the key for how this valve operates in a system. So let's get into it and take a look at it from more of a technical point of view with the schematic. So here we have the same components. We've got our canopy up here on top. We've got our bonnet, which basically is connected to the canopy, and the bonnet is usually threaded into the body. So it's physically connected to the body. Sometimes the bonnets are made of bronze, sometimes they're made of a plastic material, and they all have an air inlet valve and a seal ring that seals up against the bonnet. And there's some kind of spring in here, or springy material. It can be elastomeric, it can be a physical metal spring, but this is the key right here to how the operation of the PVB works when we start thinking about back siphonage. Remember, RPs can do back siphonage, back pressure, high hazard, low hazard, pressure vacuum breaker, back siphonage only, no back pressure, high hazard, low hazard. So that's where we're kind of looking at this valve from. Why can you not back pressure? Why back siphonage only? So as water flows up into this valve, and this is a normal operation, this seat and this check valve is going to open up right here in the bottom. That's the single check. And the air inlet valve will close and seal tight up on the top here, and water will flow out through the outlet of the valve. Normal operation, not a problem. And this is a great situation. Now we're working, we're flowing water, we're protecting the water supply. So now let's change things around a little bit with this particular pressure vacuum breaker and say, we're going to back siphon this thing, just so we understand how it works in a back siphonage situation. So now our direction of flow is out of the valve. We're pulling water this way. What happens is first is the air inlet valve. The check valve should shut. That's our number one backflow prevention device. But if this check valve is fouled, and let's just say we got a rock in there, the air inlet valve is going to open up, allowing air into this PVB. As that air comes in and fills up the void, the water that's sitting here in this backflow preventer will probably siphon a little bit, but the water coming over here will not be siphoned back into the PVB. The air will be siphoned into the PVB, and this becomes a back siphonage backflow preventer. Very unique compared to an RP. And so that's why these work very well in back siphonage situations. Now, let's take a look at how this operates in a back pressure situation. So now we're going to back pressure this valve. We're actually going to push the water back into this. And we're going to say the check valve is fouled. So we have a fouled check valve again, something in there. This back pressure can be strong enough to keep this air inlet closed. Right here, it may not open up. It should stay closed because we're back pressuring this valve. And this water will push all the way through the PVB and all the way out into the potable supply. And that is why you're not allowed to put a pressure vacuum breaker into a back pressure situation. It is not made for it. It only works in back siphonage. And so this basically, now you've got a really expensive elbow sitting in your system that's allowing a back pressure and possibly contaminated water to flow back into the potable supply. Are there any questions on the RP or the pressure vacuum breaker operation before I continue into the installation requirements? Pretty unique, I must say. All right, so now let's see how that back pressure, back siphonage conditions, how that PVB's operation and the RP's operation, how does that look in an installation requirement? And the reinstallation requirements that I'm going to cover here are the approval agency's installation requirements. So this is the USC's Foundation for Cross-Connection Control and Hydraulic Research, who does a lot of the approvals for, I would say, about 35 states in the US. So you have to have USC approval to put backflow preventers into these states. Other states require ASSE approval, and that is very similar. And so these installation requirements follow the guidelines from these agencies, not necessarily the guidelines that could be required by the local authority that has jurisdiction. So remember, it's always the local authority that has jurisdiction that calls the shots. This is what the approval agencies say. Most AHJs and water purveyors follow the approvals, and they just lockstep in line with that. So some installation requirements. We are going to cover the double check briefly because it's part of this process. And the double check's very simple on the installation. Usually they're always installed below grade in a valve box, and simple inline valve. Sometimes we see a Y strainer on the inlet. That's actually code in Texas. And there's usually a 6-inch minimum clearance from the bottom of the double check to a bunch of gravel that's down below. Really straightforward installation, not something to be too concerned about in any situation regarding a double check. Now, when we move to an RP and we start looking at the installation of an RP, it must be above grade. We've seen some people try to put them in vaults, and there are some code variances that allow that, but you got to put a pump in there and a lot of other things in order to make sure that any of the water that comes out of that relief valve does not flood the vault and cover up the backflow preventer. So let's just talk about the outdoor above grade installation like I've got on the screen here. The critical part in all of this is the 12 inches minimum above finished grade or ground level. It's the finished grade that is the key here, and it's 12 inches from the bottom of the relief valve. From the outlet of the relief valve to finished grade, it's 12 inches minimum. And then 30 inches is the maximum for the approval agency. So you got a pretty wide variation there in order to install an RP correctly. Now, note that this is a physical dimension assigned to this product. In other words, no matter how you install this RP and what kind of terrain, as long as you're physically 12 inches above the ground level, no matter where you put it in, you're following the code. So that's very, very product specific. So it's very product category specific. So it's very specific to all RPs. All right. So that's very unique when we start looking at that. And that means you can install it anywhere, which is the beauty about an RP. Not only does it cover all the applications, all the different hazards, the two types of conditions, back siphonage and back pressure, but you can install it anywhere as long as you have that 12-inch minimum clearance from the bottom of the relief valve to finished grade or ground level. Now, when we look at a pressure vacuum breaker, it's much different because this becomes application specific versus product specific. The 12 inches minimum is not 12 inches to finished grade. It's 12 inches minimum above the highest piping or outlet. In this drawing I've got on the screen, you can see that this pop-up came up 4 inches. Well, it's 12 inches from the top of the pop-up to the center line outlet of the pressure vacuum breaker. If this was an 18-inch riser pop-up, then you'd have to go 12 inches above that. If there is terrain on the property, wherever the piping is at its highest, you've got to be 12 inches above that. So it's very application specific in its installation on how the PVB should be looked at when you look at these requirements. So that's why we see pressure vacuum breakers installed in a lot of very flat lots or production homes. Anywhere where there's not a lot of terrain or a lot of elevation, a pressure vacuum breaker, as long as the code and the AHG allows it, you can install a PVB. If you've got any type of terrain or other things that you're going to be connecting to that you have to consider, then you're looking at putting in an RP. And that's where we're going to go next, is looking at, when do we select an RP? What conditions and what installation requirements are going to take us down the path of choosing an RP over a PVB? Well, for example, property elevation. I mentioned that. If you've got property elevation and terrain, the last thing you're going to want is to have a PVB 7-8 feet in the air. First of all, that would go against code. Second of all, I think OSHA would get on top of anybody that had to go service that. I've gotten pictures in emails from folks and text messages of pressure vacuum breakers that are up on the eaves of houses, because that's code, right? It's 12 inches above the minimum. And that's the problem, because it's not code. You're too high elevation on that. You got to bring that down. And since you cannot bring that PVB down because of the back pressure situation, you got to install an RP. So property elevation, select an RP when PVB gets too high off the ground. A lot of people will put in hanging baskets with drip lines. That's back pressure, RP. Elevated planters, large potted plants. I've seen, 4-foot planters and tree baskets and things. And you're like, wow, you gotta, those are a lot of times added later. I've seen people put misting devices on zone number 6 because it's not being used on the property. And so now you've got a way to control your misters automatically. And so now you're connecting to something up on the eaves, an RP would have to be put in. A big thing that we see going on is a lot of backyard remodels going on right now. And people are putting some decks in and get planters on there. And the elevation of those planters and whatever's on those decks is definitely creating a situation where that PVB is no longer installed by code. And you'll either have to raise that PVB up to accommodate that extra elevation, or an RP will be required. Remember, RP is the one-stop shop. And let's just note here is that in any situation, in all the codes that I've ever seen across the US, If you're using an automated chemical injection system, so what they call chemigation, an RP is always required. So you always have to select an RP when you have any chemical injection system, whether it's a passive injection system or an active injection system with a pump. It does not matter. If you're introducing chemicals into a pipe that's connected to the potable supply, you got to put an RP on there. There's some argument on that, but I can guarantee you go to any cross-connection control specialist or water purveyor, as soon as you say chemical injection, they are pre in their brain, as that's how it goes. RP, RP. So remember that. And let's just take a peek back to the RP again, 12 inches minimum from the bottom of the relief valve, physical, right? Physical dimension here on the RP associated with the product, not a application situation. So this makes it ideal for any installation on any application. And yeah, it does cost a little more, but it certainly is the direction that most codes are going, and most applications are requiring in those situations that we just covered. Any questions on the installation requirements for RPs or pressure vacuum breakers? It's pretty interesting stuff. Go ahead.
Paul, actually, oftentimes we run into, I guess, problems. Let's say back in Nebraska, static pressure at the houses at the spigot might actually be 50 to 55 PSI, and we run across the problems with pressure drop across the RPs. Do we have, I guess, oftentimes then they're facing the either do a PVB or they have to install a booster pump, and
right,
they'd much rather go with the PVB route than the booster pump route. Any other suggestions?
Well, I don't think double checks are allowed in that area of the country, so that would be something that you're not allowed to put in. With the pressure vacuum breaker, as long as you're following the elevation of 12 inches above the highest piping or outlet, I don't see a problem with that as long as the water purveyor allows it. So an RP, if it's code, RP's code. You got to get a variance on it to put a PVB in if the RP is actually the code. A perfect example is in the state of Arkansas, RPs are code everywhere in that state. And so no matter what you want to do in any situation, you have to design around it. For example, you were talking about the 10 to 15 PSI pressure loss across an RP. That could be disastrous for designing an irrigation system. A lot of times you see people then, okay, I'm going to go with more zones, smaller zones, in order to maintain the pressure that I need to get those last heads up way over there. And we see those changes in situations where RPs are required, and they will not allow a pressure vacuum breaker to be installed.
Okay, so do you see more and more booster pumps being installed to, I guess, design around RPs?
Yeah. That's definitely a trend that's going on. So the pump guys are really happy about that.
Okay. Cool.
Yeah. Yeah, no problem. Good question. All right, as we get to the end here and we're winding down on our hour, we're going to talk a little bit about freeze protection and maintenance. Remember one thing, that backflow preventers are life safety devices. A lot of people just look at them from a perspective of, yeah, that's code and necessary evil, we got to put it in. Okay, that's one perspective. But the reality of it is there's all these approval agencies associated with these backflow preventers. They got to go through 1-year field evaluations. There's a lot of emphasis placed upon those 1-year field evaluations. And the reason why we have all these strict codes is because these are life safety devices. They are protecting our water supply. So maintenance is really important, and freeze protection is really important in a lot of the areas that get that cold weather. And so one of the things that we all talk about during the winter, and some of these winters we've had have been very cold and brutal. Specifically lately, we had the big freeze event down in Texas, unprecedented. They don't put any protection on backflow preventers down in Houston, because Houston doesn't generally get a very cold weather down there. When it does, cold to them is usually, probably 30 degrees is cold for Houston. Well, when they hit the low teens and single digits this last winter, all the PVBs in Houston broke. I mean, it was a major wipeout, everything in the market event. And that's a problem in a lot of areas around the country where we get cold weather. We have to understand that the water in our irrigation system freezes, it expands. Not only does the backflow preventer get damaged, but the irrigation gets damaged. So there's a lot of things we've got to address when it comes to freeze protection. So backflow preventers do become damaged when they are frozen. I get a lot of people trying to return products that have been frozen and they're cracked, and there's no warranty for freeze protection that hasn't been implemented on a backflow preventer. So if you don't winterize the valve and it breaks, it's out of warranty. So the winterization is required, and that's the key part here in this slide. As we're talking, there's basic freeze protection with pipe wraps and heat tape and backflow blankets, and that's generally for areas that are in that, that subtropical or sub-Mediterranean climate where sometimes they get cold, sometimes they don't, but not necessarily are they going to be, freezing for 3, 4, 5 months a year. So in those areas where you're freezing, the top 2/3 of the United States in the northern climates, there's a 4-month freeze. It's just we go into winter. That's where the advanced freeze protection must happen, where we're doing system blowouts. The backflow preventers sometimes are removed from the system. There's a lot of different things that we do, but we have to make sure that we do our freeze protection in order to keep the backflow preventer healthy and working so that it's doing its job of protecting our water supply. A lot of freeze protection, ways of getting it done. I've got some details in other slides, but for this particular presentation, we're just talking about it from a pretty high level and just reminding everybody that that freezing does occur, and even for places like Houston, it can wipe out several 100,000 backflow preventers in a couple days. That's a lot of money and a lot of work for all of us to fix all of that. Not to mention our water supply is not being protected anymore. Maintenance. So backflow preventers, they need to be inspected and maintained at least once per year, but local codes are going to tell you what to do on what type of backflow preventer. One of the things we see specifically with pressure vacuum breakers is once they're installed, a lot of times, especially on a residential system, a lot of times people are like, all right, I don't have to touch it again. And the water purveyor's like, yeah, it's just a house, don't worry about it. And so there's a lot of non-compliance going on, and it's being wink, wink, forget about it. And that is kind of a concerning thing. It happens a lot. Not so much when you're working with an RP. And the reason why is because an RP is a much higher level backflow preventer. We see those dripping water, we see those in areas where they need to be winterized, so they are looked after much better by the service folks out there, and they do a really good job at keeping those RPs up and running. The PVBs, not so much. But approvals require them to be serviceable in line. So you should never have to take a backflow preventer completely out of line to service it. You should be able to fix it right in line. That's the way they're designed, and that's the way they've been approved. And then some areas of the country require backflow testing on all backflow preventers in any one given area. A perfect example is the city of Indianapolis. They actually have a backflow testing code throughout the entire city on all pressure vacuum breakers, and they have to be tested every year. You get out into some areas of Virginia or even down into Florida, and you test it when you install it, and then you walk away from it. And if it ever has problems again and needs service or maintenance or replacement, then you test it again. But until then, it could be years that go by that the backflow preventer has never been looked after. Happens all the time. So those are kind of local code things that go on, and we just got to know that each one of these backflow preventers can be serviced in line, can be tested, and should be tested and at least maintained so that we know that they're working properly.
Hey, Paul,
Yeah.
question. When we were always trained during winterization to always leave the ball valves at a 45-degree angle versus fully open, I guess, do you guys, I guess, is there a reason for that?
Yeah, so it's a good question too. So the question here is basically the 45-degree open close, half open, half close on winterization for ball valves. And yes, what happens is there's a little socket or little pocket behind the ball and the cup which is the plastic cup, the Teflon cup inside the ball valves, and water can get back behind that. It always does. And when you shut it off or leave it all the way open, water gets stuck in that one little area. At a 45-degree angle, those ball valves are open to atmosphere behind that little area, and that little piece of water that gets stuck back there is now allowed to expand and go into atmosphere versus freezing, causing the ball valves to crack. And also, you have to think about it from a perspective of, hey, I've got all these test cocks, all 4 of them are quarter-turn ball valves. So a lot of people forget to do the 45 on the test cocks, and you end up losing a couple every year. And then once you learn that process, just go through and winterize those test cocks just the same way.
Okay.
Yeah, good question there.
Coming out of winter, that's where we oftentimes will get spider webs in between the bonnet and the canopy, and then people are wondering they can't get their PVBs to seal. And it's like, well, pop off the canopy, clean that up, and you should be good to go.
And that's it. That's the basic maintenance that I'm going to cover right now. And that is, just get in there and inspect the parts for wear or damage, clean it out. A lot of backflow preventers, they just get debris and little things and particulate buildup, mineral buildup. And, all you really need to do is get in there and clean them. A lot of times you can throttle the inlet ball valve, and if you're open to atmosphere or free flowing, or you got a whole bunch of zones going, or a big zone going, or a hose bib open, you can throttle the inlet ball valve. It causes some disruption in the backflow preventer. Sometimes some of that particulate can go blow right through the backflow preventer pretty easy. Or if you can get that relief valve to dump on cadence by opening and closing, your number 3 test cock, you can get stuff to dump out, and you can clean out the valve that way. But generally in the wintertime, when you do winterization, that's the perfect time to get the backflow preventer inspected, replace any rubber goods, and then look at it and get it ready for the install for the season.
What's the normal lifespan for the rubber, all your rubber in those?
It depends on the water quality. Some areas around the country where they have decent water quality and not a whole lot of mineral in the water, we end up with, a couple of years on rubber goods without any problems. You get down into Florida, they got a lot of chloramines in the water, very aggressive water. You're replacing rubber goods quite often, annually, if sometimes.
Okay.
Yeah. And that brings me to the end. If there are any other follow-up questions, now's the time. We just clipped over the 1 hour, and probably IA wants me to close out, but if you got questions, we got some time.
What do you normally do for, how do you inspect a double check valve, a dual check?
That's a good one. Dual checks are generally, you test it. First thing you do is you hook it up and test it. If you test it and it passes, you're done. If you test it and it fails, then you got to open it up and start looking at the checks inside. And then it's just like anything else, it's inspecting and sometimes it's replacement. But for double checks, you just gotta test it. And that's a big problem. And that's why double checks are becoming outlawed in a lot of places, is because you never know if they're working or not. I mean, it's like here in Idaho, they grandfathered in all the double checks for all time. I guarantee you half of them aren't even working. They need to go implement now a testing program. Same thing in Texas. They need to implement a testing program to go test all of them just to make sure they're operational.
First system I put in, I mistakenly put in a dual check. So it should have had something else.
They still use those little dual checks down in Georgia.
Minimum, basic tools. What basic tools? So if you're a service tech, what do you recommend having in your toolkit?
Generally, just screwdrivers, wrenches. Mechanics set. Sometimes there's some specialty tools out there you can buy to remove seats. So seat tools are very important. Each one from each manufacturer. That's the problem. Is that like an auto mechanic, you got the Toyota tool, the Ford tool. It's the same thing in backflow prevention. You're going to have some specialty tools. There are some third-party companies that make those, but you're working in plumbing systems. So talking pipe wrenches, large crescent wrenches, adjustable wrenches, things like that. If you're in the testing world, you need a backflow test kit. Yeah. And gauges are really handy. A lot of people don't carry gauges, and the reason why they're real handy is you can diagnose things real quickly. Just a simple 0 to 200 psi pressure gauge, or 0 to 100 pressure gauge with a 1/4 inch national pipe thread on it, where you can screw it into a test cock and turn on the test cock. That way, at least you can look at the incoming pressure, each test cock across the valve, whether it's a PVB, you can look at the inlet, the outlet. If it's an RP, you can go down the line. Same thing with the double check. You can look and see the pressure in each area, and you can run the valve, you can run the system, and you can look at the pressure drop. So at least you get some analytics that you can start making some technical decisions without just taking things apart.
Cool.
Paul, I had a question. This is Greg. I was curious if there was any sort of online certification for backflow testing, or if you knew of any list or online area where you can go to look for your local testing facilities and things like that.
That's a great question regarding testing. So it's going to be specific to any one given area or region around the country. So just note that the certification codes vary like backflow codes vary. And in any one given area, you'd be looking in your local region. So where are you located?
I live in San Diego.
Okay, so in California, lots of options in California because it's a very big backflow state. You've got the American Backflow Prevention Association, ABPA. They put on classes, and they're really good at that. Also, the USC approval agency at the University of Southern California, they have classes out in California. Sometimes you can find your local plumbing union will do classes through a community college. That's pretty popular across the whole United States. Also, there are some third-party guys running around in the Southern California region that offer classes that are very competitive in price. And remember, when you go through these processes, it's 40 hours is the requirement, whether you're doing it across 1 week, 2 weeks, or a month. It's 40 hours of instruction that includes both hands-on and the textbook instruction. And the test is both hands-on and written. So that's pretty strict requirement on that. They don't make many variances. I know across the whole United States, that's a pretty big headwind for a lot of people to take 40 hours out of their work week to go get certified. But it's a good thing. I mean, if you're in the service industry, or if you're in a landscape service or irrigation service, putting backflow testing into your service card and what you're offering, very big advantage versus a lot of people who do not do that, or people who sub that out to independent backflow testers and repair folks.
Oh, really appreciate the information. Yeah, we get a lot of customers that come through the factory for training and other things on irrigation. I work for a hunter, and they always ask about it. They say, well, hey, how do I get certified for backflow testing and stuff like that? So it's good information. Thank you.
Yeah, if you shoot me an email, and I'll bring up my my contact slide again here. Shoot me an email, and I'll give you a list of everything I got for in your area, people you can contact, and move forward with getting your certification.
Appreciate it. Thank you so much.
Yeah, not a problem.
Any last questions for Paul before we wrap up?
What's that?
I was just asking if there's any last questions before we wrap up. All right, well, with that, that does end our backflow session for today. Thank you all for joining in for the Backflow Prevention for Landscape Irrigation session, and a big thank you to Paul for leading this great session. Our next webinar will begin at 2 p.m. Eastern, and that is our Marketplace Trends and Regulatory Update session. As a reminder, that session will have its own unique Zoom link. Again, thank you, Paul, and thank you to our sponsors, Rainbird, Hunter, Ewing, and Brightview. Thank you, guys.
Thank you. Thanks, everybody, for getting on. Have a great afternoon.